Hello and welcome to 2.3, calculating limits using the limit laws. So we start off with our limit laws. Okay, there are 5 of them. Okay, it says that suppose that c is a constant and the limits of x approaches a of f of x and limit as x approaches a of g of x exist. Then we have these following rules, right, these laws. So the first one is the sum of the limits law. Okay, so if you have the limit of the sum of two functions, you can say that this is the limit of the first function plus the limit of the second function. Okay, likewise you have the difference law. Okay, so if you have the limit of a difference of two functions, you can take the limit of the first function minus the limit of the second function. Okay, if you have a constant times a function, you could take the limit of the function and then just multiply by the constant. Okay, if you have the limit of the product of two functions, then you have another way to say it would be the limit of the first function times the limit of the second function. Okay, and then if you have the limit of a quotient of two functions, you could take the limit of the top function divided by the limit of the bottom function. Okay, as long as the limit of the bottom function is not equal to 0. Okay, and then these are the verbal versions of the same laws we just talked about. Okay, you guys can pause the video and read them if you like. Okay, but they're the same 5 laws we just discussed. Okay, so let's take a look at our first example. Using the limit laws and the graphs of f and g in figure 1 to evaluate the following limits if they exist. Okay, so f is the function in pink, g is the function in blue. Okay, so let's take a look at the first one. Limit as x approaches -2 of f of x plus 5 times g of x. Okay, so what we could do is we could state that this is, we could use our sum law. We could say this is the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5 times g of x. Okay, and then what we could do further with this 5 times g of x, we could use our constant law. Okay, that would be the third one. Let me just rewrite the first part. X approaches -2 of f of x plus, take the constant, we would say 5 times the limit as x approaches -2 of g of x. Okay, so let's see what happens to the function f of x as x approaches -2. Okay, so x is -2 here. Alright, so what's happening to that function? Okay, so it looks like it's approaching -1, right? Even though there's a hole at -2, okay, the function holds this value, but the limit is approaching this value, so that would be 1. Okay, and let's take a look at g of x. Okay, for g of x, as x approaches -2, looks like it's approaching -1. Okay, so that would be 5 times -1. Okay, which gives us -5. So we have 1 minus 5. So that means overall our limit would approach -4. Okay, good. Let's take a look at the second part. Limit as x approaches 1 of f of x times g of x. Okay, so as x is approaching 1. Now for f, looks like f, it's approaching, so we could just say that this is going to be the limit of the first function times the limit of the second function. Okay, so for the first function, for f, looks like it's approaching 2. Right, as x is approaching 1. Now for g, as x is approaching 1, well, it looks like there's no agreement, right? So from the right, it's coming and it's approaching -1. From the left, it's coming down and it's approaching -2. Okay, so there's no agreement there, so there's no limit, does not exist. Okay, so whenever that happens, then your overall limit will just be a does not exist. Okay, so for that one, the limit for the product does not exist. Okay, let's take a look at our next part of that example. Limit as x approaches 2 of f of x over g of x. Okay, so another way to write this would be limit as x approaches 2 of f of x divided by the limit as x approaches 2 of g of x. Okay, so 2 is here. So for f, if we're approaching 2, looks like it'll be about 1 point, it's above 1, below 2. I'm going to say about 1.5. Might be even less than that. It's close though, it's 1.5. For g, okay, g is approaching 0. Okay, so we have a divide by 0 scenario, and we know that we cannot have that, okay, in any situation. So when we have that 0 in the denominator, this ends up becoming the limit does not exist. Okay, so any questions, just bring it up in class through WebEx or email me. Okay. Alright, let's take a look at our next slide. Okay, we have the power law. Okay, so these are some additional laws. If you have a limit of some function where it's a function raised to the power, okay, you could take the limit of the function itself okay, and whatever that is, and then take the result and raise it to the power. Okay, so that's our power law. And then we have a couple other laws. The limit of c, okay, so limit of a constant, right, will be the same constant as x approaches a. If you have the limit of x and x approaches a, then you'll end up with having a. And you just replace x with a, and you end up with your limit equaling a. Okay. Any questions on those, just bring it up. We'll talk about them. Okay, some additional ones. Okay, if we put f of x equals x in law 6 and use law 8, we get another useful special limit. Okay, if we have a limit as x approaches a of x to the n, then we end up with a to the n. And we just replace x with a, and we end up with our limit. Okay, similar limit holds for roots. If you have x approaches a of x to the nth root, just replace x with a, now you have a to the nth root. Okay, so the root law, if you have the limit as x approaches a of the nth root of f of x, we could take the limit of our function, okay, and then take the nth root of that. Okay, so that would be the root law. Okay, the direct substitution property, okay, which we'll talk about in further detail. Okay, so if we have a polynomial or rational function and a is in the domain of f, then we could just take and use the direct substitution property. Right? Plug in a into your function, and we end up with our limit. Okay, and this is just stating a fact we used the other day. The left side and right side limits have to agree for our two-sided limits to exist. Okay, so the limit as x approaches a of f of x equals our limit if and only if the left-sided limit and the right-sided limit are also equal to our limit L. Okay, so let's take a look at example 2. Limit as x approaches 5 for our polynomial. Okay, so we could use the direct substitution property here and just plug in. Okay, so we would have as x approaches 5, so everywhere there's an x, plug in 5. Okay, so we have, and once you do the plugging in, next you want to do PEMDAS, right? So first do the exponents. 5 squared is 25. 3 times 5, 15. Plus 4, 2 times 25 is 50. Minus 15 plus 4. Addition and subtraction is left to right. 50 minus 15, 35 plus 4, so 39. Okay, for our problem on the right, limit as x approaches -2. Okay, it's a rational function. We could plug in though. Let's see. So we have -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times negative 2. Okay, again, evaluate using PEMDAS. You have exponents. Negative 2 cubed is negative 8 plus negative 2 squared, that's a positive 4. 2 times 4 is 8 minus 1 over 5. This is like negative 3 times negative 2, that's a positive 6. Okay, simplify the top. We have negative 8 plus 8. Those are opposites, they'll cancel. Minus 1, so we have negative 1 over, and then 5 plus 6, 11. So negative 1 over 11 will be the final answer. Okay, example 3. Direct substitution doesn't always work. So what happens is sometimes you could end up plugging in directly and it's not going to give you an answer. Right? If we plug 1 in here, we get 1 for the top would be 0, and then 1 for the bottom would be 0. We get 0 over 0. Okay, well, that's not going to cut it. Okay, so what we do is we use a factoring technique. Right? We could factor out the top. Okay, x squared minus 1 is a difference of squares, which means we could factor it and get x plus 1 times x minus 1. Your denominator is x minus 1. Okay, and once you factor, you'll notice that you can cancel out a common factor, right, top and bottom. Okay, and now you can look at what's left and then apply the limit. Okay, so we have just x plus 1 on top. Okay, and now we can apply the limit. So plug in the 1, direct substitution, and we end up with 2. Okay, so that'll happen sometimes. You'll have to factor in order to avoid the the 0 over 0 or the divide by 0 scenario. Okay, let's take a look at example 4. Find the limit as x approaches 1 of g of x, where g of x is defined as x plus 1 if x is not equal to 1, and pi if x is equal to 1. Okay, so what we have here is like almost like a piecewise function. You want to picture your function basically as you have a graph of it. It's x plus 1 when x is not equal to 1. So x plus 1 would look like, well, we got a y-intercept of 1. It's a slope of 1. So in general, it'll look like this. And then when x is 1, it's equal to pi. So when x is 1, pi is going to be like slightly above the 3. So that means we'll have a hole there. Okay, so what would be the limit as x approaches 1? Well, if we looked at what 1 would bring us, this is approaching 2. Right? Even though I drew it slightly off. Right? If we plug 1 in here, 1 plus 1, that gives us 2. So this function is approaching 2. So just like we looked at in the previous section in 2.2, you want to look at the general trend of the overall function. Okay, so even though there's a hole there, we still know that we are still approaching the value of 2. Okay, so when x is 1, we end up with 2. So the overall trend would be a limit of 2. Okay, let's take a look at example 5, simplifying the function. So here we can simplify this a little bit, and then we could apply the limit. Okay, most notably we have this quantity in parentheses. Okay, so we could expand on that. 3 plus h squared. Okay, so that's going to be like saying 3 plus h times 3 plus h. Okay, and right off the gate, we're doing this because if we did the direct plug-in of 0, we got to divide by 0 in the bottom. Okay, so let's see what happens here. If we expand on that, we'll do a FOIL. We have 3 times 3, that's 9. 3 times h is 3h. H times 3 is 3h. And h times h is h squared. Okay, we have to divide by h. Okay, so let's combine any like terms. We have h squared. 3h and 3h is 6h. We have a plus 9, a positive 9, and a negative 9. They will cancel out. Okay, all over h. Okay, so notice what we could do here. On the top, we could actually factor out an h. And by doing that, we'll be left with h plus 6. And then what can happen next is we can cancel an h, the h from the top with the h from the bottom, because those are like common factors now. And so now we're left with limit as h approaches 0 of h plus 6. Okay, now plug in the 0. Okay, 0 plus 6. So we just end up with 6. Okay, let's take a look at the next one. Calculating a limit by rationalizing. Okay, sometimes you'll use this property of rationalizing. Sometimes we call it rationalizing the denominator. This time this will be rationalizing the numerator, okay, because the numerator has the rational piece to it. The square root is in the top. Okay, so when we go to rationalize, let's write the original function first. Okay, so what we'll do is we'll multiply by top and bottom by the same two terms that we're rationalizing, just opposite sign in the middle. Okay, so we'll have a t squared plus 9. That's the term in the square root. Opposite sign, so instead of the minus we have the plus and the 3. And we multiply top and bottom. like that. Okay, so for the top, okay, what we'll do is we'll do like a FOIL on this. Okay, so the square root of t squared plus 9 times the square root of t squared plus 9 will just be t squared plus 9. Okay, the middle terms would cancel, and then we have negative 3 times positive 3, so that would be negative 9. Okay, the bottom, you have t squared times this quantity, so let's do t squared times square root t squared plus 9 plus 3. Okay, the plus 9 and the minus 9 will cancel in the top. So we have t squared over t squared times the square root of t squared plus 9 plus 3. Okay, so we have a t squared top and a t squared on the bottom. Cancel those out. That'll leave you with a 1 on top. So we have limit as t approaches 0 of 1 over square root t squared plus 9 plus 3. Okay, so plug in 0. We could apply the limit now. So we'll have 1 over 0 squared plus 9 plus 3. So that gives us 1 over square root of 9 plus 3, which equals 1 over square root of 9 is 3 plus 3, so 1 over 6. And that would be the final answer. Okay, so that's rationalizing the numerator technique to figuring out the limit. Okay, let's take a look at our next example. Finding a limit by calculating left and right limits. Show that the limit as x approaches 0 of absolute value of x equals 0. Okay, so to do this, we're going to look at the graph of absolute value of x. Okay, so you guys will remember the graph of absolute value function is a v. Okay, and the limit here as x approaches 0, what we'll do is we'll break this apart into two limits. And we'll look at what's happening as x is approaching 0 from the left, and what's happening as x approaches 0 from the right. Okay. So we see that the limit as x is approaching 0 from the left well, from the left, this is approaching 0. So we'll say our function. Okay, the limit as x is approaching 0 from the right of our function is also 0. Okay, so the two sides agree, so we see that the limit as x is approaching 0 equals 0. Okay, let's take a look at our next one. Prove that the limit as x approaches 0 of absolute value of x over x does not exist. Okay, so for that one, let's take a look at the graph. Okay, so here's the graph. We'll also take a look at the algebraic portion. Okay, so we clearly see that the two-sided limits do not agree, right? So from the left, it's approaching -1. From the right, it's approaching 1. Okay, well, let's see how this happens with our notation. So if we do limit as x is approaching 0 from the right of absolute value of x over x, well, from the right, when x is positive, absolute value of x is going to stay as x. Okay, so we have x over x, basically. Limit as x approaches 0 from the right. Okay, which will end up becoming limit as x approaches 0 from the right. Now x over x, that cancels. Right, those two cancel. You're left with 1 over 1, which is 1. Okay, and the limit of that constant will be 1. Let's take a look at the limit from the left. So limit as x approaches 0 from the left of absolute value x over x. Okay, so when x is less than 0, right, absolute value x is going to behave like -x. Okay, more importantly, what happens is absolute value x is going to be x, right? But on the left, x itself, the bottom x, is going to turn negative. Right? That's basically what's going to happen as you go to negative numbers. Okay, what's on top will still stay positive, but what's on the bottom, that x on the bottom will turn into a negative number. Okay, so when that happens, we can reduce again. Okay, we end up with 1 over -1, which is equal to limit as x approaches 0 of -1, which equals -1. And so because of the two-sided limits does not exist, does not match, right? We got the one limit to be 1, the other limit to be -1. Therefore, this limit will not exist. Okay, so any questions on that, just bring it up in class or email me. I'll be glad to answer your questions. Okay, let's take a look at another example. Greatest integer function is defined by, we got these double square brackets. It's equal to the largest integer that is less than or equal to x. Okay, for example, 4 in brackets equals 4. 4.8 in brackets equals 4. Pi in brackets equals 3. Square of 2 in the brackets equals 1. -1/2 in the brackets equals -1. Show that the limit as x approaches 3 of x in brackets does not exist. Okay, so for one of these things, let's take a look at the graph of it. So here's the graph. Okay, this is known as a step function. Okay, you guys can see the steps there. Sometimes this greatest integer function has these other notations. Okay, so sometimes you'll see it as a single square bracket. Sometimes you'll see it as a bracket like these L's that are almost like mirror images of one another. And it's sometimes known as a floor function. Okay, and the floor function name probably makes a little bit more sense. Basically, you're rounding down, right? So if it's 4 would just stay as 4. But it's 4.8, you're rounding down to 4. 3.14, you're rounding down to 3. Right? Square of 2, which is 1.414, and it goes on. Irrational would round down to 1. Okay, so it's the largest integer that is less than or equal to that number. Okay, so show that the limit as x approaches 3 does not exist. Okay, so as x approaches 3, we could show that the two-sided limits do not agree. Right, so if we're approaching 3 from the left, we end up with 2. So limit as x approaches 3 from the left of it's approaching 2. Limit as x approaches 3 from the right. Now from the right, it's approaching 3. Okay, and so because the two-sided limits do not match, then we could say that this is a does not exist. Okay, questions on that? Bring it up in class, or you could email me. Okay, calculating limits using the limit laws. So if we have a theorem such as f of x is less than or equal to g of x when x is near a, then we would say that the limit as x approaches a of f of x would be less than or equal to the limit as x approaches a of g of x. Okay, so it just makes sense. If one function is less than the other function, the limit of the lesser function is going to be less than or equal to the limit of the greater function. Okay, the squeeze theorem. Okay, this is a squeeze theorem, and it more applies to g of x. If g of x is between these two functions, so it's bigger than f of x, but it's less than h of x. Okay, and if you know the limits of f of x and h of x to be some limit, then g of x, okay, whose value is between f and h, g of x would then also be forced to be the same limit. Okay, here's a little graphical representation of that. So here is g in the middle. It's greater than f. Okay, it's less than h. Okay, and the limit at a for both h and f happen to be L. So g then therefore has to be L as well. Okay, sometimes it's known as the sandwich theorem or the pinching theorem. Okay, our book calls it the squeeze theorem. Let's take a look at an example of that. How to squeeze a function. Show that the limit as x approaches 0 of x squared times the sine of 1 over x equals 0. Okay, so now if you remember back to last section, we looked at the sine of 1 over x, and it was this oscillating function. Okay, and the values of sine oscillate between negative 1 and 1. That goes between negative 1 and 1. Okay, so basically, you're basically looking at this function as some value that's going to go between negative 1 and 1. Okay, so in the worst case scenario, it's a negative 1. Okay, which makes it look like if it's a negative 1, this turns into negative 1 times x squared. So we have negative x squared. And then we have our function here, x squared times sine of 1 over x. And on the greatest possible value, it turns into a 1. So that means it'll be on the greatest, it'll be turned into an x squared, because then it'll be 1 times x squared. Okay, so basically you have x squared times sine of 1 over x is going to be greater than or equal to negative x squared, but at the same time it'll be less than or equal to x squared. Now what happens to these two functions as x approaches 0? Well, if we look at the graphs, right, x squared is the parabola opening up, negative x squared is the parabola opening down. Okay, we know that at 0, both of these functions are going to be 0. And so by the squeeze theorem, we could say that the limit as x approaches 0 of x squared times sine of 1 over x is also going to be 0. By the squeeze theorem. Okay. Alright. Any questions on this, just let me know. Email me, bring it up in class. Have a good day, have a good night. We'll see you soon.